Swayam Prabha. Digital India. Educated India.
So now we'll see this other part, some more kind of thumb fun days, and then we start application. Okay, so next little bit of important concept is this derivative along the trajectories. Okay, let me get the slide more. Okay, so as you can see here, the derivative along the trajectory is a concept for developed for the same function v. Okay, so if v is given as the function, get the mouse right, of time t and vector rn, vector belonging to rn space, and it's a real, I mean it's a real valued function here. Okay, taking b, finally getting the value to be in the real space. It's continuously differentiable with respect to all arguments. This is one condition that is necessary here, that it should be continuously differentiable with all arguments, and del v is denoting its gradient with respect to x. Okay, this is written as a row vector. That's another kind of a small thing. Then the function v dot defined by this way. Okay, so what we are doing here, if you see the v being function of time and this vector, its differentiation will have a time part plus this vector part and multiplied by del v by del x or dx by dt, because this is a complete derivative. So del v by del t, okay, plus del v by del x into dx by dt, and del v by del x is actually this del v. Okay, the gradient del v. Okay, so this part is fine, but what we do here is for dx by dt, which is x dot, we are actually substituting our system. Okay, so so this is a very important part here, that we are taking the derivative along the trajectories of a system. Okay, so if you generally see this v function, it can have derivative in many different directions. This is a directional derivative. Okay, so since v is a function of this vector Rn space, this derivative is a directional derivative. It's a vector function, so it will have a derivative which is directional derivative, and we are taking it in the direction of the trajectories, direction given by these trajectories of your function or of your system. Okay, the system is defined as x dot is equal to f of t comma x. Okay, because we are substituting that x dot here, we get this derivative which is along the trajectories of the system for this function. Okay, so let me explain you this concept a little bit more in detail here. So so if you have this Vx now, let's consider the two state systems, the x1 and x2 are only two states for the system. We have defined this V to be positive definite function in some way. Okay, so I'm considering this kind of a bowl nature for this V, and if I'm at any point on this V, okay, whatever point I am, okay, then at this point I can define derivative in many directions on this x space here. Okay, so so along some direction, so if you map this point on the plane, you'll get some kind of a directions for the derivative. Okay, so I can ask, okay, what is my derivative along derivative of this function along some direction here in the x1 x2 space. Okay, now this particular direction that I am choosing to define is a trajectory evolution of this system on this space plane. Okay, so x dot t is actually giving me a derivative of this kind of trajectories which are evolving. Okay, so so when we put we take a derivative along this, so we substitute this x dot into our equation for v, then actually we are kind of getting the derivative or this the way the function is evolving, or the derivative of function is going, or the tangent to the to this v surface is a tangent to the surface along the direction of these trajectories. Okay, so that is a kind of a notion that gets into. And if you see for these things in terms of okay, so this so in terms of system dynamics, if you see the system dynamics evolving here in some kind of a way, like when that system dynamics trajectory is mapped, like or projected on this v surface, then along the system trajectory direction, what is happening to v is what we are actually eventually getting. So that is a kind of a concept for derivative along the trajectory. Now how do we see the stability of system based on these condition? So suppose like we are considering the same kind of a system, x dot is equal to f of xt, and then the equilibrium for the system is 0, and total energy is 0 at origin and positive otherwise. So that is we know this energy function has these properties that we want for this say function candidate v. So v is considered as an important function in the Lyapunov theorems eventually. So you say that okay, there exists such a v in such a way that some conditions will come. Okay, so this v Lyapunov function candidate is important, and energy is one of the possibilities for considering for this v. Okay, so we see this kind of idea in first in terms of the energy, and then we can argue some of the things. Now system is perturbed from origin, and we start observing. So system is perturbed at say some point from origin, okay, at this point, and now we see okay, the system kind of trajectories evolve, and we see what is happening to my v, okay, or what is happening to my energy E. So first case, say energy is non-increasing, okay, so energy remains there. So I'm perturbing here, and the energy is same, okay. So v is equal to 0. Okay, what it means is that the system trajectories will not leave this v level, and they will keep on the system will keep on oscillating in the as projected on the this phase plane. You see that the trajectories are going in the circles. Okay, then if you see the other condition, okay, this is kind of a stable also in the sense of Lyapunov definition. Okay, you remember that epsilon delta definition. It is this system is stable in that sense. Okay, although we may consider from the perspective of linear system, this is like a marginally stable kind of a behavior that one can see. Although other thing is this what we are talking is of the equilibrium, stability of the equilibrium. Okay, in the Lyapunov we don't say the system stability, because the system may have many equilibria. Okay, so in the nonlinear systems, in linear systems we have only one equilibrium. Okay, so we don't have any problem, but here in the nonlinear systems there are many equilibria that are possible, and we talk of the stability of the equilibrium rather than the system. That is another important point to make sure. Then if you have a energy of a system monotonically decreasing, okay, so from here energy at some this is along the trajectories, and it is decreasing along the trajectories. The energy of a system is kind of decreasing, and and eventually going to zero. As you see, these trajectories are so what we are doing is we are actually getting conditions from without the solution in place. Okay, so what we are looking at is just a v dot. Okay, v dot is less than 0 or not. Okay, so we are not really looking at it as if it is solution is available and we are projecting the solution and we are seeing that. No, what we are getting these conditions directly based on the v dot computation as per this previous kind of a formula. Okay, so this is a v dot. We can compute v dot directly and conclude something based on this about v dot, right? We don't need really the solution of the system to be there. Okay, that is the beauty of this theorem, that okay, without solving a system we can kind of do some kind of a predictions about the stability part. Okay, so this I am showing you the solution just for the sake of understanding here that okay, if it is monotonically decreasing energy along the trajectories, so some kind of a evolution will happen here. We don't know that, we need not know. As long as we know that v dot is getting less than 0 happening along the trajectories, we are fine. Okay, so if that is the case, that means some way the trajectories are kind of approaching this equilibrium position 0. And then if it is increasing function, so this becomes then the stable and attractive kind of equilibrium, and that's what gives you this asymptotic stability. Okay, and when this is increasing, you can see that if this is increasing in the direction along the surface of this v, then your trajectories are going away from it are going out of the bounds, probably bounds of whatever, they are not coming back to the equilibrium 0, and the system is having that unstable kind of a behavior. Okay, so these are the basic foundations, the fundamentals for this Lyapunov theory. Okay, so we can so this derivative of energy type positive definite function is 0, the equilibrium is stable. Then if it is strictly less than 0, then so this derivative, the derivative of energy type function, okay, if this is strictly less than 0, then the equilibrium of the system is stable and attractive, which means it is having asymptotic stability, and there is this there is definite relationship between the stability and the properties of V. Okay, so this is some kind of a sketchy kind of a analysis to say that. Okay, and there is more formal kind of a mathematical formulation Lyapunov has proposed and come up with the theorems on stability. So the idea here is not to restrict ourselves to only energy type of functions. You can define any function which is PDF. This is another kind of a beauty of Lyapunov theory, that you don't restrict yourself to only energy type of function. Any function you can take if you are able to find these. So these are, so Lyapunov gives all the necessary conditions. Okay, so if you are able to find whatever satisfying the conditions, then you have a result. So if you are not able to find, we cannot say. Okay, those are kind of conditions that typically the theorem has. Okay, so these are one way kind of arguments. Okay, so if you are able to give me these conditions satisfying B or other kind of a function, whatever it is, then I can guarantee you that your system will be stable or asymptotically stable or whatever. The stability definitions will come for the system. Okay, so that is the idea that Lyapunov has proposed. Okay, so we'll see one or two theorems and then we'll close for now. Okay, so this first theorem of stability proof. Okay, no proof here. We are just going to see these theorems now. Okay, the proof is there in the books if you want to get into, but as a part of this class, we are see this. Otherwise, this again Lyapunov theory and it's all these theorems becomes like a matter of discussion, long discussion in maybe a half a semester kind of a course can be there on the all the details, nitty-gritty of definitions and mathematics. Okay, so we are right now looking at more mainly application perspective for this. So this why we are not getting into too many mathematical details, but just the essential kind of details, so that we can look at these theorems and apply them for a case that it's at our hand. Okay, that is the whole idea of development here. Okay, so this theorem on stability says that equilibrium zero of this system. Okay, so this system, as we saw earlier, that okay, we define the system such that the equilibrium is zero, and this equilibrium zero of the system is stable if there exists LPDF, like like locally positive definite function, which is continuously differentiable at least once. V, which is again defining based on this t and x here, and real valued function. Okay, and constant r greater than 0, such that this v dot of x is less than 0, less than or equal to 0. Look, this sign is not less than 0, this is less than or equal to 0, and for all t greater than t0, and for all x belonging to ball of radius r. Okay, so this r constant is defined in the way that we have this condition valid at least for some distance or some kind of a norm around the origin. Okay, for that this is valid. Then we have the equilibrium of the system. Yeah, so v dot is evaluated along the trajectories of the system. Then this equilibrium of the system is uniformly asymptotically stable. Okay, this is equilibrium stable system is stable, sorry. The v dot is evaluated along the trajectories of the system, then this equilibrium is stable. Okay, so there are these conditions which are putting a condition on v dot to be less than or equal to 0. Okay, so this is important condition here. So you define some kind of a v which is positive definite function of so it needs to have all the components of x represented in the function, okay, to be LPDF, as we have seen in some examples. Okay, so you define some function. Okay, it need not be energy function. Energy functions is typically the first candidate that we should try, but it is not mandatory that it has to be energy function, no. So when we do our Lagrangian formulation, already we have energy expressions available, so that becomes like a naturally the first kind of a candidate to consider there. Okay, so that's why this is connected, that D matrix is kind of very important for these Lyapunov theorems when we start using V as a energy function for our mechanical systems. Okay, then we have this definition of stability when v dot is less than or equal to 0. Okay, so you need to establish that v dot is less than or equal to 0 by same kind of arguments of say either quadratic function or your basic definition of LPDF and things like that. Okay, all right. Now we have this uniformly asymptotically stable kind of a definition coming up here, where now we have this exists decrescent LPDFV. So now this is decrescency condition is coming in addition. So this function beta of class K is an upper bound. You remember that decrescency we talked in the last part is about existence of this function beta of class K such that the V is bounded from above also by this function. Okay, so that is are bounded from above by this function, and the bound from below is actually coming by the definition of LPDFness for okay. So if that kind of a thing exists, then it is uniformly okay, so so this is a condition on V, and for asymptotic stability we need this minus V dot is an LPDF. Okay, so this is now a little stronger condition than V dot is less than or equal to 0. So now we want this V dot minus V dot to be an LPDF function. So you check this minus V dot function and see that it has this property of LPDF, where you remember the properties, like we have a V, so this minus V dot should be 0 here, it should have some evolution such that it is bounded from below by some function of class k. That is what will these properties of this v dot will be, minus v dot will be. Okay, so you need to make sure that LPDF properties are satisfied for this minus v dot. Okay, LPDF at least in some ball of radius r where r is greater than 0. Okay, from the origin you take some kind of a norm up to the point r, and then in that to that thing it should be valid. Okay, then that equilibrium is called uniformly asymptotically stable. Okay, so there are more kind of these definitions. So what we need to bother about is this asymptotically stable system and a stable system. These are the two main kind of points we take from here. There are more kind of a finesse to these definitions: asymptotic stability, uniformly asymptotically stable system, or exponentially stable system. All these kind of different definitions are theorems are there, which we are not getting into more details. What we are interested in to see is that this system is stable or asymptotically stable. The asymptotic stability is a stronger condition to have, because in asymptotic stability we actually look at the system trajectory is going to 0. So like that we'll see. So we'll talk about this and more examples from the next class onwards, and application from the next class onwards. Okay, so you can meanwhile try to apply it to this case, okay, and see whether you are able to kind of see through so don't look at this directly. You can apply yourself to our simple kind of a case of mass lying on the surface, to get a hold of get a hang of how things work here. And we'll anyway discuss in the next class. Okay.